Hello, everyone. Um, I'd like to tell you something a little bit about a string theory and parallel universe and extra dimensions. But actually, what happened by saying all these things, I end up getting kicked out from the physics forums and astronomy forums for doing this because I was accused um, of propaganda of pseudoscience. So they say that it's a science that isn't well, it's not a science really. It's just a sort of what's it called? Uh, Not really much of a science at all, according to um, calling a string theory a theory. But one thing I'd like to explain something interesting about string theory. String theory is a theory, but is it a good theory or not? That's the question. And is it a is I know it's there's a lot of it, a lot of stuff in it that talks about parallel universe and extra dimensions, which a lot of people cannot accept. And I don't, I'm not nothing against that. They don't have to accept it. But if you remember theories, any theory, even like let's take for example, even the even the expansion of the universe and the Big Bang, it wasn't known during Einstein, and even Einstein thought that the universe was static. Uh, but his theory of relativity was predicting that universe is not static; it's expanding. But he could not believe that, and he didn't accept, and that was his biggest blunder. So, see, the funny thing is, a lot of theory is always ahead of experimental physics. So you see, we came up with this new theory. Like this, you can look at the past mistakes people make, calling like even the Higgs boson that was discovered just recently. It was discovered in 1960s. Uh, not discovered, theorized by Peter Higgs, and he predicted a Higgs field. There is must be a Higgs field, but he was not proven until recently when the big collider was built, LHC, in in Geneva. So you see, it's been only proven now. It was found. The Higgs field was found. They didn't know whether it existed or was just a theoretical thing. So you see, there's a lot of people that attack the theoretical physics, but theoretical physics is always ahead of because imagination is always ahead of experimental. Because if you cannot imagine of what can things can be like, uh, it would not it would not move the science forward. People all stuck to say, "Oh, the universe is so limited," because they think that you have to be proven by experimental. But if you remember, Jules Verne 2000 Leagues Under the Sea, the book was written when there was no submarines, and he was the first who wrote about Captain Nemo and his submarine. So, and that was in 1800s and something, and at that time there was no submarines, but he wrote about it because he imagined it. So you see, and Einstein, proving Einstein, don't prove. A lot of people say Einstein, like want to disprove Einstein, but he said he was correct. He said imagination is more important than knowledge. You see, imagination is we're getting these people who called who said that theoretical physics is a pseudoscience and attack theoretical physics and say that basically they disrespect Einstein because Einstein himself said that imagination is more important than knowledge. Being because without imagination we cannot come up with the new ideas about things, and then we can test these things. So you see, sometimes practical physics, experimental physics moves forward with sometimes, yes, sometimes there's experiments that cannot be explained by theoretical physics, but sometimes, but most of the time, it's a theoretical physics that comes first, and then we get and prove it by the experiment. So you see, with string theory was in 1970s. It was discovered. It was and then because it was discovered in 1970s, and a lot of people and there's a lot of stuff. Why is the string theory is not a boner? I can tell you, a lot of people say it's just rubbish. It's there's no experiment can prove it. But we'll get to that yet. But why is string theory so important? Why is it important to physics, and why is it? It's yes, it's a theory, but why is it so important? It's because string theory is important because it's you see there's a calculation with there's a mathematical problem with quantum field theory. Quantum field theory explains that point particles has infinite momentum if you calculated that over the stretch of the universe. But anyway, yeah. So there's a mathematical problem with it creates a lot of there's a try to if you try to explain what the momentum of the of the point particle is in a space-time, it will give you an infinite actually, you know what, actually when you try to combine relativity and quantum mechanics, the point particles create infinities. The calculations create infinities for point particles. That's why people came up with the string theory. They say, okay, let's just have a look at this little piece of a rope sort of thing. Let's say particle is not a point, because like not just a point, but let's imagine it's a rope, not a rope but a band, like a little tiny band or string, that's what they call it, which vibrates. And because of that's get rid of the infinities uh, in mathematical calculation, and combines quantum mechanics and gravity, not gravity, sorry, combines quantum mechanics and relativity, you see, but practically gravity, yes, but yeah. So you see, it gets rid of this problem where we cannot combine two theories, which explains the big and explains really small. We could not combine these two theories, and actually no other theory here, no, there's no other theory better than string theory that can explain all forces of nature together. But there's a problem again with the string theory, which a lot of people use this as they call it a pseudoscience, because you see, string theory combines gravity, relativity, and combines quantum mechanics together. It explains all four forces of nature. String theory does. There's no other theory that can explain it, but string theory does. But it creates the problem with multiple dimensions and parallel universes. See, it all came out of the string theory. It didn't come out on its own. To have some mathematical calculations to be correct, you need to have for the string to move through space in a certain way, or in the particles to act in a certain way. We needed the strings to have a multiple strings, tiny strings, exist in a more dimensional universe. So you see, this is a problem with this is the problem with a string theory. It's not a problem. It's in the mathematics, and it's possible. The funny thing is that the problem is we cannot prove it yet. That's the biggest problem at the moment. But there is a start. So you see, and it's also quantified the gravity. So the gravity has particles gravitons. So according to string theory, the gravity has also particles graviton, but they're really heavy and they're really small, and actually they're massless particles like light, but we cannot it's very hard to detect them. So needs a big energy accelerators bigger than that. Not so right now we don't have a technology to test this. However, in the future, I think pretty much in the future we will be able to test this theory for whether it's right or wrong. I don't know, but hopefully in the future we will be able to find find the graviton particle. So you see the yeah. So the gravitons yeah the gravitons is the particle. It's the particle that explains the gravity, the field of gravity. So we need to find this particle. So that's what we're gonna be looking for in the future, hopefully. And but the string theory, as far as it goes, even though parallel universes people may not believe in them, but according to string theory, that there is a parallel universes. The strings can create a part this parallel universes, which actually in fact created a Big Bang. It explains the theory of Big Bang, and I think it also explains the theory of inflation, and also dark energy. But again, it needs to be tested against the yeah, against the theory. Or any theory needs to be tested. For now, at the moment, we don't have the technology to do that. However, just because we don't have a technology doesn't mean the string theory is not correct. The funny thing is, with the string theory, what I find very amazing is that the mathematics is just it just explains all forces of gravity, all forces of nature. That so all attractive forces, the weak, the strong, electromagnetic, and the gravitational force. It combines all the forces of nature. There's no other theory that can do that, and that means that if it can do that, if string theory can do that, it means that we are closer to unified field theory. So unified, so all one theory for everything. We are closer to that. And you see, yeah. So string theory is, yeah, it takes us much closer step, and of course it's theoretical because people use imagination, and there is no limit to imagination compared to the effects of what we can observe in the universe and what we can test against test tool. That limits our, our imagination. Our limits are what we have because we don't have a technology yet. So, but also, yeah. So string theory and also parallel universes. I'm not sure about, yeah. Parallel universe is very hard uh, to find, but I'll tell you an interesting theory. There's also a theory that explains that there is a parallel universes. That, for example, in relativity, it's purely theoretical. You can look it up on the internet. But one thing about parallel universe, which is interesting, is that every we know this. We have a frame of reference. People, you travel with a, for example, if you every time you fly in a plane, the plane warps space time. You see those experiment by two physicists in 1970s when they took a atomic clock into the plane, two atomic clocks set to exact the same time. Atomic clocks means they run very very accurately without, like, I mean very accurately. There's nothing more accurate than atomic clocks because they tick due to the atomics decay process. But anyway, um, yeah. So one was left at Earth in somewhere in the United States, and the other one was set to the plane, and plane went around the Earth in one direction twice, I think, or once, I can't remember, and then it went to the other. And then there was landing. There was a third clock. They took another clock and went different direction. And all these clocks, three clocks, one was left at the United States, the reference frame, and the other two was measured at different time frames. So there was a different time in nanoseconds. Of course, nanosecond is not a big time, not a big difference, you would say, but it is makes a very good prediction of relativity. That relativity is correct. And so anyway, so what I'm trying to say is that because that actually proves that the plane warps space time. So you see, every time you'd go in a plane and travel um, to different location and you warp space time, you actually not travel into the same your universe. You travel into a different universe. In fact, I know it sounds crazy, but um, the theory is that you can that the parallel universes, there's many, but because you warp space-time, you see, you in a different reference frames. Time is like another dimension. Think about this. Time, we know that there's a three space dimensions and a time dimension. And time dimension, because it's a dimension. Think about it, this nanoseconds difference makes you in a different place. Displacement. So there is a displacement in time for you. Some people say this is just a relativity, but no, it's not. It is a relativity, but every time you know your parents go when the plane, or someone go, or you travel on a plane to different, your reference frame is changed to the reference frame on the Earth. So you are now in a different reference frame, and your time ticks differently, and you actually travel into different universe, parallel universe. You to say, the reason why I'm saying this is that because if you travel with the speed of light, not the speed of light, even half of the speed of light, across the universe, into the different, you actually travel. You don't travel in time. I mean, you do travel in time, and you also travel in a parallel universe. I don't know how more to explain this, because your time it's also another dimension, and that means there's a difference between the original, where you came from and where you're going. There's a difference in time. See, the time is another dimension, and because there's the difference in time, that means you travel into a different universe. See, because if you come back, and like you travel and then you come back, you're still young, and everyone got old. That's not the same universe as you left. This is not the same. This is, you travel through many, many, many parallel universes, which you know like tick every time, every, and that's not made up idea. This is a quantum theoretical calculations. There's a quantum decay because of the wave function. Sometimes it collapses, and sometimes it's just, so you see, in quantum mechanics there's this uncertainty. The same thing is with this theory. It's actually not my theory. I didn't make this up. I read it somewhere. I can't remember who said that, but who, I think it maybe was, what's his name? No, I think it's Stephen Hawking with someone else was debating this. Anyway, so yeah. So anyway, there's about wormholes and stuff. But this is what they say. It's not my words. They say that that every time you travel on a plane, or when you travel at a certain speed of light, or close to speed of light, you should travel in a different parallel universe, because when you come back, everything, it's not just relativity, but, and there's many, many parallel universes, through time and stuff. But anyway, yeah, this is just one idea. I know it sounds crazy, but anyway, this is yeah. So every time you warp space-time, so warping is possible. You see, every time plane goes around the Earth, or whatever, or the space station goes around the Earth, the time is different. There's a time dilation in nanoseconds, maybe, but they do warp space time. So if they warp space time, that means that they can travel to parallel universe. Not just the theory of relativity is correct, also the fact that they can travel through different universe. I know it sounds you know fetchy and stuff, but that's just the sum of the theoretical explanation of the parallel universes. So I think I'll leave it at that. It's been a long time, 20 minutes talking about this. I think I had to get it off my chest, because I've been attacked by people, I don't know, trolled out and attacked by people on physics forums for saying these things. I'm sorry, I didn't mean to hurt anyone. I just want to say that, yeah, I mean, because where are we going? It's just our universe is shrinking. It's like we're not, because of this, people will say, oh, I'm gonna stick with the ideas, with these ideas in physics. We're just gonna stick to the observation. But how far can we observe? Can we even, when we look it up in the sky and see the furthest cluster away from us, like, what is it, 13 billion light years away or something like that. Even that is not truth, because that cluster existed 13 billion light years or 13 billion years ago. The light travels from that cluster. Even that is not true. Every time we're looking out in the sky, we see almost into the past. We see what the universe was like millions of years ago, not what it is like right now. So my point is that the only way to move forward, and I always like physics, because theoretical physics especially, because people can come up with the ideas, because what moves us forward, ideas. The ideas are born, even if they're wrong ideas. The main thing is that they are born ideas, and the ideas, and then we can say, oh, okay, this is a good idea. Let's just test this. Let's test this idea. Let's see if it works. And then it works, and then and then say, oh, then becomes a theory. And then we say, and then there's ideas that are born, and not even though they're not correct, we learn from the mistakes. So okay, so this is not a good idea, so we just leave it. It's not, or it's been tested and it hasn't been proven. So it said, oh, this idea doesn't work, so we throw it out. Well, not throw it out, but we say, okay, this, we can make something out of it. But the main thing, the imagination of people moves us forward. Imagination, that moves physics forward, moves science forward. We can create them. First we imagine it, and then we put in maths, and then we test this, and then that's what moves the progress forward. If you closed in your universe, say, I'm just gonna stick to observation, you just sort of lock yourself in this little space of yours, in your narrow-minded universe, and say, that's and then you attack everyone who try to get you out of this box that you're in. So yeah, so this is where I want to live it. I want to live it that theoretical physics, it's not a pseudoscience. It moves progress forward, even though any ideas are welcome. Any ideas people make, they must be welcomed, because instead of being attacked and called the monkey business or something, but any ideas needs to be tested. But people need to this is what moves the science forward, not anything else. Like Einstein said, imagination is more important than knowledge. Okay, thank you very much. I'm gonna leave it at that. My head is on fire. Thanks.